Okay, so good morning, everybody. So let me start saying the obvious, okay? That is that developing new measurement capabilities is fundamental to advance our understanding of the physical world, okay? So perhaps the best example, current example is LIGO, okay? That is this laser interferometer gravitational wave observatory, okay? So the story I will tell you today in particular is going to basically tell you a little bit about our attempts trying to uncover entanglement from entanglement, okay? So what we are going to do is we are going to exploit the entanglement in the probe, okay, to essentially extract entanglement from the target matter, okay? So this is work, I'm a theoretical physicist, okay? But, in order to make real advances in this particular attempt, I have to work pretty close with experimentalists, okay? So, and I've been working really for 5 years because we have to develop instrumentation, et cetera, to do this kind of thing. Okay, so the work I'm talking about will focus mostly on trying to unveil correlations in matter, but indeed, some of these ideas can be used and have been used, for fundamental physics tests, okay? So before, I go to the detail of the talk, that essentially what I will do, I'm going to answer these two questions that are here written there. Can one realize this entangled beam of particles? Okay, that's the first question. And the second is what kind of useful information we can extract using these things, okay? So why, since this is a kind of new set of ideas, I have to motivate a little bit, okay, this kind of thing. So what I'm interested in here, okay, probably the same kind of thing that you are all interested in here. That is, we want to develop ways of learning about the intrinsic entanglement in some particular states of matter, in particular strongly correlated states of matter. Okay, so for example, I'm interested because I also work in this field on frustrated magnets, quantum spin liquid phase, unconventional superconductors, topological states of matter. And indeed, the obvious thing is that the probes, the experimental probes that we have, although there are many advances, okay, they are very limited because most of these states of matter are extremely strongly entangled, and it's very hard to come with local probes, the standard local probes, and extract information on those states. So the question is, okay, what happens if we try to use now and do something on the probe itself? So what happens if we try to entangle the probe, to craft that probe to a particular observable, and then try to uncover entanglement from the target matter? Okay, that's the idea. Of course, this is an open-ended, type of subject. I will just show you a little bit of what we've done, okay? Because I'm not going to show you all the things we've done, but just a little bit. And the question is, okay, so when you entangle the probe, what kind of information you can get? Now, what is a probe? The probe in principle can be anything, can be neutrons, can be photons, can be X-rays, electrons, atoms, quantum dots, and everything you can imagine you can entangle. Because what I'm going to tell you today is just, entangling beams. And the main reason why I started with this particular framework is because, indeed, I wanted to use these big facilities, okay? Because this is a kind of professional type of thing. So we want to work with national labs, and we want to set up these things for users, okay? So now, indeed, what kind of thing I'm interested in? And as I told you, I would like to have some direct proof of multipartite entanglement in materials. Oops, sorry. Indeed, this is ideal. Typically, most of the probes, they test, just 2-point correlation functions. So if we can find ways of probing multi-point correlation functions, that would be great, okay? I'm not going to show you that part because that's pretty hard. Why? Because if you want to test multi-point correlation functions, you need a probe that can entangle in particles. So I could do that with photons if I have entangled photons, and indeed I have a large flux of entangled photons. Then I could use these ideas, and the theory is there because it's very easy to do theory, okay? But it's hard to do experiments. But we are working on that. And then, you know, issues about fundamental tests that I'm not going to talk about here, because there are interesting things you can do with these entangled probes to test fundamental physics. Now, let me give you a flavor of what I mean by essentially using entanglement in the probe. So imagine you have some exotic material, but this exotic material has some sort of correlation length. Okay, so there is a kind of correlation length characteristic of this material. This could be, you know, some dimer or whatever. You have some random dimer or whatever you have there. Now imagine that you could construct a probe that is entangled in such a way that this entanglement also captures, or you can tune these some particular length scale that I will call psi, or I will call this entanglement length. Okay, so you can imagine I drew here some of these things because these are all the tests that we have performed in different configurations. But you could imagine that the probe that is there is nothing other than something like that. Okay? I will explain a little bit more. Now, you can imagine that if I can adjust this entanglement length and I hit the characteristic correlation length of the dimer, something may happen. Of course, the whole point is that this must be a coherent beam. Because indeed, you need to construct a beam that is fully coherent, because otherwise, you know, I mean, it's something completely incoherent and it's not going to capture, okay, the characteristics of the correlations in the material. So, so basically, this is what I said. And in how many ways you can use these ideas? In this, I can identify 3 different ways. One way is just use interferometry, in which case, if you want to probe correlations, you will have to think a little bit, what is the best entanglement witness that you can develop, okay, to characterize those correlations. That is, you know, is an industry. So you've seen in the first lectures on quantum information theory, you've seen some of those entanglement witness, you know, the CHSH. That now is called, this combination of operators now is called witness. So why is a witness? Because that particular crafted correlation is special for certain states. Those states are the maximally entangled states. And if it turns out that you can maximize those correlations for those special states, you can use this to your advantage because you can falsify statements. Indeed, these kind of ideas we have used to write protocols to falsify Majorana, the existence of Majorana fermions, for example. You can write this. This is a technique that is coming from quantum cryptography that is called quantum self-testing. Nice. So another way you can use that, this is the way I will tell you today, is by using entangled probe scattering. So you may think about this kind of thing as a weak measure. That's what it is in the end. Or you can think a la LIGO, okay? And when you think in a LIGO, what you are doing is metrology, quantum metrology. So you may think that you can entangle your probe in many different ways to get more accurate results of your measurement. And there are protocols to do that.
Sorry.
Yes.
Are you saying that your probe is better than CHSH?
No. I would say that my probe, I'm going to test that it can use, you know, CHSH to prove that it is entangled, but then I will show you what is information I can extract. I didn't tell you what I can do with that probe. My first task is to prove that I have those probes. Because one thing is to say, you know, to do theory, but then I need to prove. So this, okay, I will have to indeed, otherwise, you know, yes. So if you want to learn, there are many articles and there are many others. I didn't put here on these things. Okay, this goes, you know, this is an effort that is only for the things I'm going to tell you here. This is essentially is a sample of the people. There are lots of experimentalists. I mean, I'm the only theorist with my students working on this thing. So let me, oh, jeez. So let me now try to go to my first question. Can I realize these entangled beams? That's the first question, because theoretically I can, but experimentally is not obvious. So indeed, one of the first things I concentrated on was trying to use neutrons. Why? Well, because there are lots of experimentalist neutron scatterers in our department, and it's a very good way of advancing the field if you have the people close to you. And all these people have connections, to the usual facilities. So, but to do that, indeed, you have to create new instruments because, those neutron beams are coming from nuclear reactors and, they produce the beam, but those are not entangled in any possible way. Okay, so you will have to create some entangler, and that entangler requires an instrument. So the instrument that our experimentalists developed is called magnetic Wollaston prism. So it's not a coincidence. This is like a polarizing beam splitter in quantum optics. It's the optical equivalent. So where essentially the magnetic field, since the neutron is a particle without charge and has spin, is essentially the magnetic field plays the role of the index of refraction, if you want, or refracts, photons, light, or whatever. So I'm not going to go in detail how is that you construct and what is the math that you have to do to model these instruments. But the whole point is that this instrument, essentially what it does is to create a beam that has these features. Essentially, you may think that this beam is entangling, this is like a wave packet of the neutron. This is the same neutron, okay? This is the same neutron that is here and here, where essentially this upper path has a spin up and then the lower path has a spin down. So essentially the state that is claimed that this instrument is generating is something like that. So this looks like a Bell state, okay? But I have to prove it's a Bell state. So indeed, you can do the same thing with something called RF flippers. With RF flippers, indeed, you can do similar kind of things, but you can do one more thing, because you can adjust the frequency of these different, flippers. And it turns out that if you detune this frequency of the secondary flipper by delta, you can also entangle in energy. So essentially, you can produce a state that is like this, like a GHZ state, okay, that is entangled in this particular way, okay? Again, you need to prove that this is true. Okay, nice. Now, there is one more thing that is important to mention is that if this delta is not this delta, this is a transverse width of the wave packet. So the delta in the frequency there, if I put it equals to 0, it functions exactly the same way as a magnetic Wollaston prism. So if I put delta equals to 0, I go to this state here. So the same instrument can create this or that. And that is great because when I am going to make a test, I am going to check by doing that, and it's better that, the two witnesses I'm going to do, I violate both, okay? So this is just to give you an idea of what is the size of these instruments, nothing else, okay? These are the RF flippers. This is the line, the neutrons are coming, through this line here, and this is the size of people, so you can see more or less. So now, what is my task? My task is to develop these instruments, to develop these interferometers. These are like Mach-Zehnder type interferometers. And when I have these interferometers, I need to essentially put these interferometers in what is called neutron spin echo mode, essentially. And it's pretty similar to the Hadamard that we were seeing today. You were showing a Mach-Zehnder. This is, also some sort of Mach-Zehnder. And essentially what you do is, in this particular case, there is a neutron beam coming here. This is essentially what we claim that we have here, the Bell state, the state like this, okay? Then what we do is we need to modify the phase, the relative phase in the spin sector of this beam. Then I have to modify the relative phase in the path sector. This is done with that. And then I essentially echo. This is the other Hadamard, okay? And I put these two beams together and I just measure here. For the RF flipper, is something similar. Nice. Of course, you can write down all these interferometers, okay? You can go and translate the action of each of these things in mathematical terms, and this is exactly what happens, okay? So each pair, for example, of Wollaston prisms, this is essentially, oops, sorry. each pair of Wollaston prisms is essentially this entangler. And when I do in inverse mode, this is the inverse of that thing. Okay, and you see that the phases, the relative phases I put in the middle of interferometer will show up as this total phase here. The same is for the three parties, okay, for the GHZ state. Nice. So I am not going to say, because I was told to explain contextuality, I don't have time to explain contextuality. The only thing I want to say is that the inequalities we are measuring here are contextuality inequalities. They are not Bell inequalities. Okay, because to have Bell inequalities, you need a space-like separated things. So all experiments that are done in quantum optics where they are measuring Bell inequalities, I mean, they are essentially doing contextuality inequality. Contextuality is more general, but I just want to remind you that the only thing, and this is fundamental for quantum mechanics, the only thing that contextuality means is that there is no predetermined values to the things that you are observing in your system. That's what it means. Mathematically, it's hard to prove, although I put in here, this is a very beautiful explanation by David Mermin, I mean, using this context. There are 6 contexts here, okay? And then you can convince yourself. If you want, you can go to the questions and I can. Now, I need to construct the witness, and the witness is a CHSA witness. It's exactly the same thing. And indeed, this witness, the only thing I need to do in my interferometer, I need to adjust, okay, these alpha angles, alpha and chi angles, and these are the choices I made. So for those of you that know, when you look at these Bell inequalities, you do sigma Alice dot A, sigma Bob dot B. This A vector, B vector is this spaces here, okay, with those angles. So these are the angles that we manipulated experimentally, and indeed the classical expectation that it should be smaller or equals to 2, and the Bell state, or any unitary rotation of the Bell state, should produce a 2 square root of 2. Now, someone asked a question, can we generalize these witnesses to higher, number of qubits or even higher dimensions? The answer is yes. The answer is yes. It's very simple for more qubits. This has been done by Mermin, but if you have qubits, whatever, you will have to work harder, but you can still do it, okay? So of course, you will have to recognize what are the maximally entangled states that you want to certify. That's the thing. So indeed, this is the Mermin witness that we use, and the classical value should be smaller or equals to 2, and essentially what we get is a 4, if it is a GHZ state. Nice, these are the experimental results. We tried neutrons with different wavelengths, we tried different deltas are, psi are this spin echo length here. So we try different distance. You have to change the magnetic field of the Wollaston prisms or whatever there. Okay, so we try different things. And indeed, what you see, when you measure all these different conditions, this is a maximally entangled beam. It's a coherent beam. That's what you prove. So at that moment, you can say, well, we have that probe. Okay, and indeed, we have that probe also for the case of the tripartite, that is for the GHZ state. So we also have there, a GHZ state. So we can play with the either, with this beam or those with this beam. Okay. So now we have a universal probe for quantum materials. What can we do with that? That's a question. Oh, this is a recent experiment. It's not published. We also did this case. Okay, that is in spin and energy. I just mentioned because this paper is going to appear soon, and it's beautiful, also works. And here you can explore correlations in the time domain. Okay, that's the important thing about this particular configuration. What is it useful for? That is a question that I want to address in the next 5 minutes, quickly. Okay, so here, this is an open-ended question because there can be many answers. I will show you one of the things that we found, okay? And essentially what we have to do is to reformulate the theory of scattering, okay? Because the theory of scattering, if you go to any textbook or even papers or book on scattering or whatever, 95% or 98% of the presentations are plane waves. We cannot do that. You are going to find papers where there is a wave packet, okay, it's a harder calculation, but nobody does this with entangled beams. Okay, with entangled beams, if you put entangled beam, there is no calculation because no one thought about that thing. That's a reality. Okay, so the setup is similar. And okay, you are going to use some generalization of the T-matrix formalism. Okay, in the Bohr approximation, I mean, it's the usual thing, but there are some tricks. That mathematical tricks you have to see in the paper. I'm not going to tell you how you regularize the things, et cetera, but it can be done. Okay, and indeed, what you want to measure in this case is scattering the differential cross-section. Okay, so the differential cross-section is what the experimentalists measure, and what they measure is how many neutrons, I mean, the count rate that you have here per unit solid angle. Okay, and that's essentially, you know, you can filter in a spin, you can do many different things, but these are the different differential cross-sections. Now, these differential cross-sections are related to correlation functions, of course. Okay, so our beam, I go quickly. This is the same thing as this. Okay, let me go fast here because there is no time. And now I am going to make a possible application. So what I'm going to do now, I'm going to generalize the Van Hoff theory. The Van Hoff theory is a usual theory that tells you that if you look at neutrons, okay, and neutrons, as I said, these are particles that have no charge, have a spin, they interact magnetically in a particular way. This is the way neutrons interact, okay? This is the way neutrons interact in matter. I mean, when you look at the interaction of the neutrons, it turns out that if you look at the differential cross-section, the differential cross-section is proportional to the magnetic structure factor, okay? It is like, you know, SS. Correlation, 2-point correlation function, okay? So if you, I mean, here, the only thing I'm showing you is that if you are, you know, just using the standard Van Hoff theory, what you get is this magnetic structure factor where you have the momentum transfer and the energy transfer. That's it, okay? Now, if you are using the entangled probe, or let's say the wave packet, the expression for the differential cross-section, this is the differential cross-section, indeed is a little bit more involved. Okay, because now you have to integrate over the momentums, okay, that your state has. It's not just that you have a plane wave with a single momentum, okay? So, what is the difference when you have, when you have a beam like this? So this is the case of a beam like this. When you have a beam like this, what you are going to see is that this magnetic structure factor has terms that are indeed like interference terms. Okay, and those interference terms will depend on the entanglement length because they have phases that have to do with entanglement length. So essentially what happens is that you have a very structured beam that interacts with a piece of matter, and this response that is still for this beam is a 2-point correlation function, but it's a 2-point correlation function that has interference terms that is coming from all this entanglement. Okay, and you see that these phases can be changing this distance here. Okay, so nice. So let me show you some results. And these results, just to give you a flavor, these results essentially will tell you that what can you see? Suppose that now you have a dimer state. You have a dimer, you know, a dimer, I mean, it's a simple state that has, you know, triplets or singlets. Okay, and it turns out you could imagine that your state of matter is a random set of these dimers or whatever, doesn't matter. But the dimer has a particular length scale, and your probe has 2 additional length scales, the width and this distance. So there are 3 length scales in the problem. And there is a competition, and depending what you have, you will see different things. So imagine that you have, you know, something that is delta goes to infinity. It's like a plane wave, but they are separated the plane wave by this distance. Okay, imagine this situation. That's what you see. So it turns out that if the dimer is in a maximal entangled state, the state is, the response is insensitive to the distance. It doesn't matter. But if it is not maximally entangled, it matters. So for example, this is a maximal, the red is a maximally entangled state. These are different distances. You see, it doesn't change. It's always the same. But if you take a state that is unentangled, like the blue, this always changes, depending on what is the distance. So imagine now that you have a quantum spin liquid, and this experiment will be done soon. It will turn, I mean that, you know, if you see that the response does not depend on that, that means you have a liquid. Okay, let me go quickly. This is the most spectacular thing you can see. The most spectacular thing you can see is when you are working in a particular landscape. So when this scale here is like this, this is of the order of that, it's not very large, okay? So now it's not a plane wave, okay? And now let me illustrate just with a movie what happens. So if my dimer is in an entangled state, what you are going to see here is that this is like a standard Young-Lee experiment. It's something similar. You will see some interference pattern. But if this state is entangled, you wash out all these things. There is a quantum erasure, okay? That would be beautiful to see experimentally, okay? So these transitions, now you are going to see here like a double slit experiment type of thing, okay? And now if the initial state is entangled, what you see is you see the forward scattering here at the center, okay? But then you will see that the information is washed out. Okay, so that is beautiful. Imagine you have a double slit experiment, but it's not classical. These are entangled slits, okay? You wash out, you don't see anything. That to me is extraordinary. I was not expecting, I mean, now in retrospect, doesn't seem so silly, but this is spectacular. I'm not going to explain that. I am going to skip because it's already late. And let me tell you what other things we've done. We've done many other things. Some of the things is now we say, can we create beams with orbital angular momentum? So I have these things, but on top of that, I want to create orbital angular momentum. That is very interesting. And in quantum optics, it's a big subject, okay? With vortex light and with all these kind of things. Indeed, you can use this instrument to do this thing. We've done, this is theory. Let me show you. In theory, what you see, this is beautiful. You change, you see all these patterns. That's what you measure. Well, this is theory, eh? This is not what you measure. This is what is theory. The experiment has been done a month ago. Oh, and by the way, there is also orbital angular momentum in the beam. This is orbital angular momentum. This is a spin. So you can imagine that this could be used for experiments, okay? I mean, it's kind of obvious application. The experiment has been done a month ago. This is a theory prediction. This is the experimental result. We have not used this beam yet. Again, the paper will appear, but to me, it's too good to be true. As a theorist, I mean, I see this is fantastic, but you know, to see experiments that give you that is highly non-trivial, okay? By the way, they measure all the spins in all directions. This is not an artifact algorithm. This is the real measurement of the spin, okay, of the neutron. Fantastic. Take-home messages. We have a universal probe, okay? We are now thinking about using the similar things with photons, okay? And there is a scattering theory, but there is much more that needs to be done. And there are many things that needs to be done in this field. This field is, you know, is virgin. I mean, it's an open-ended thing. It's open to your imagination, okay? Indeed, you know, something that we are also doing is using this in reflection mode. So you can imagine now you have a surface, you use these beams that are entangled in reflection mode, and you want to get information about the surface. You can. You will see soon. Okay? Of course, we are talking to condensed matter experimentalists like Colin Brohon, because, you know, we want to test quantum spin liquids and this kind of thing. And of course, you know, I will stop here because it's already too late and I see the chairman that is coming here. But I would like to close thanking the organizer for the invitation, and for putting together this great meeting.
Thank you very much for an excellent talk and for finishing on time. Questions? Sorry.
So first of all, when you do such scattering, you said you want to reformulate the scattering theory. What about optical theorem? I mean, the scattering amplitude itself will be problematic.
The optical theorem is satisfied, but the information, the important information is in the other part. Okay, it's in the scatter wave. That is where the optical. And by the way, you can, I mean, I told the experimentalists, but this is hard to do experimentally. So you can also do a scattering the usual way, but you can get a little bit more of information if you put some another, pair of Wollaston prisms. You do like echo in scattering, but you will have to put many. I mean, the experimentalists told me, no, this is too much.
Other questions? Yeah.
So in the picture, that schematic picture video that you saw, so it's like that if the target is entangled or it's not entangled, the different entangle. So is it like that? It depends on the entanglement length. I mean that correlation length of the beam. I mean it will react differently if the target is entangled.
Yeah. The final answer, the intensities, the interference depends on all these things you said. But there is one thing I didn't say because I didn't want to enter into the discussion. How do I know that it's probing entanglement? Well, what I am using is something that was not explained here, okay, in the lectures. That is, I'm using something that we developed with Manik Neil, I mean, long time ago, maybe more than 20 years ago, no, 20 years ago, that is called generalized entanglement. Okay, so we don't define entanglement with respect to a particular, tensor product decomposition, but we define entanglement with respect to sets of observables. That is what you measure. So the quantity, the measurement, let's say the way you quantify entanglement is by using purity. It's called purity. It's not the purity you were talking about here. We call it purity because that's the way in algebra is called. Okay, it's a purity. And the purity is a quantity you can normalize from 0 to 1. And it turns out that all these matrix elements can be related to purity. And this is where, you see what is going on. But yes, I mean, the answer will depend on what are you using, yes.
So one more, like you said, like the probe is universal. So in the sense that it doesn't matter the mechanism you use, or it just depend on the entanglement length between the two beams, or you use neutron beam or photon beam, does it matter? Or
yes, absolutely. Depends, because what this entanglement length is doing is probing the length scale of your problem. So it will depend. You see, if you have a state that is a dimer is this size, but the entanglement length is like that, it's not going to have a lot of signal, right? But if you are hitting and you resonate with that distance of that thing, it will have a larger signal. That's the point. By the way, it's important to understand the following thing. The neutron is here and here. It's hard, experimentalists don't see that.
Okay, we have a question there.
I would, very nice work, but I would like to get a very theorist point of view of the overall idea. Like when you say entangled probes, could we connect it with correlated measurements or bell-like measurements in which the two measurement operators are actually entangled? And here the probe is like the information in the system is transferred to the probe. Like the probe is a pointer here. So the basis of the probe is like the pointer, and the change of that is the information that you are getting. Like,
absolutely. I mean, I didn't have time to say that. There was a slide there. But I'm not going to alienate the chairman. So we can talk like that. But there was a slide that was saying that I can translate all these things in quantum information interferometric language. And this is exactly what that plot of interferometer have a bell measure.
okay, thanks.
Gerardo is a model speaker. Everybody, please learn from him.
No. Sorry.
So I'm going to be a model audience. I have only 4 questions. So very short. So the first one, there is this theorem of monogamy. So if I have a non-entangled probe, A and B are entangled, and now I send particle C that would like to measure B, then C entangles with B, which destroys the entanglement between A and B. So here in your probe, you perform measurements, so the entangled pair sent.
Not a pair, it's one neutron that is mode entangled. Okay, no, it's a good question. I can answer this question.
You destroy the entanglement in the system, yes?
No. So this is important. And this is important in any case for any interferometer. Okay, it's not just for this one here. There is an assumption in an interferometer when they are sending light or photons or whatever. There is assumption, I mean, and this assumption needs to be falsified, of course. There is the assumption that your particle, whenever it's going in, okay, is spending some time, but there is no collision from something else. So in the interferometer, you have to think that is on average like one particle per time. Okay, otherwise it's hard to follow because otherwise this is not true. Now, how do you know this is true or not true? Well, you have to do all these tests. That's the whole point. That's the reason why you do this test, because I could, you know, I could just envision theoretically any weird thing, but it's not true because my instrument is not doing what I think. These are thermal, almost cold neutrons. So you see, you are not sending, you know, you are not sending many neutrons at the same time. Yeah.
Second, quick. I mean, you stopped me when. Precisely.
In the target.
Precisely,
In the target.
Thank you.
Yeah. But this is not the projective measurement. This is a weak measurement.
Okay,
Remember
so it slightly destroys the entanglement. I mean, if you carry on with your detector entanglement, then it comes on the expense of entanglement in the system.
Yeah. I mean, it's called weak measurement. I think.
Okay.
Yes, absolutely.
Yeah. Second question. You showed in the movie that because the probe is entangled, this interference pattern is washed out. Now, if I look at that, I can find 100 other reasons why interference pattern is washed out. I mean, be my guest. I can write to you immediately. So is it a proof of anything?
No. This is a theory. I am not. I mean, what it's proving is the thing that maybe is not surprising to you, but is surprising to many of the neutron people. Okay, that if I give you, I mean, the hydrogen atom of neutron scattering is a diamond. Okay, it's a hydrogen atom. Okay, so because that's the smallest, let's say, magnetic system where you can probe, you know, singlets or triplets or transitions between these different states, and you can imagine you have a Heisenberg interaction or whatever. Now, what they always see, and this is in their head, and they knew this, I mean, by the way, I mean, by heart. They say, oh, you do this calculation, you are going to see like a young slit experiment, interference. And to tell you the truth, I didn't have that intuition because to me, young slit is two classical openings. There is a wavefront, comes, and then, you know, there are these waves coming from there and you see two slits. I did a calculation and yes, it is true. Okay, so I learned something. Yes, I learned something they told me. But when I put something now, a state that is entangled, and they were never thinking in this way, and I put a probe that is entangled and they didn't see anything, they said, this is wrong. And the reason why that happens is because the two spins that are coming there, they are orthogonal, you know, it's up and down. But when it's entangled, that orthogonality doesn't change. And this is surprising.
I know I will get a penalty, so I'm stopping.
Let's move on. Let's move on now. Okay, so let's thank Gerardo again for a wonderful talk.